I think I had made a mistake, by the way, early on. Like in the very beginning of the lecture, I had crossed off like testing of correlation, but then when I got here, I realized I actually kept those couple slides. So there is just, for a second, like how do we test correlations? This was the last thing we were talking about is sort of, stating the null hypothesis for a correlation test, and stuff like that. We're testing the null hypothesis assumption here is a sort of linear independence assumption. And if that were true, right, that rho equals 0, it means there's just no correlation, right? Correlation is 0. Bless you, by the way. I didn't hear you, but I saw you. Bless you. Anyway, and if the null is false, right, all it tells us is that the correlation is not 0. That's just why the correlation is typically tested in this sort of two-tailed way, right? If it's negative or positive, as long as it's different than 0, you could reject the null and have a significant correlation. Just as a point of reference too, like there's different ways of doing this, but how it can be done is that there's really one of two main ways. Either you look up a table of significant correlations where they give you, degrees of freedom and what correlation is significant at that degree of freedom. You just simply look up the correlation in that table. Or you can convert the correlations to t's and look it up in a t table. And this is sort of the equation for doing that. And just to give you an example, in our example, we had a correlation of 0.713. So talking about 0.713 times. So our overall n was 21 countries. So that means we have 19 on top. And then 1 minus r squared. So r squared is, we'll talk about that in a second, something called the coefficient of determination. So we take 0.713 and we square it. We get 0.508. So 1 minus 0.508 here on the bottom. All right. And that will give us a t value. So 1 minus 0.508 equals, so this is then 19, so 0.713 times 19 over 0.492 will give us our t value. So 19 divided by 0.492 equals 38.618 or something like that. If I take the square root of that, oops, this ends up being 0.713 times 6.214, something like that. It's 0.713 times 6.214 equals, that can't be right, 0.713 times 6.214 equals 4.430 or something like that. Oops. $431. All right, so that's our t value. We can look up a t critical value that's in those t tables. You look it up with degrees of freedom. If we do that with 19 degrees of freedom, we get 2.09 as a critical value. I'm not going to focus on t critical values and that kind of stuff. I just want to get an idea that we can actually take the t values and test them, or the correlations and test them to see if they're significant. And a lot of that, what we're going to do when it comes to reliability and that kind of stuff, is use correlations to find out there's relationships between items or between scales. So it's good to know if they're significantly related. And so since, I guess this has 6.9. So somewhere, did I screw that up somehow? I may have, let's see, 19. So this is one of those occasions that always crack me up where I am working out through problems and disagreeing with myself. Because at some point earlier on, this is my own lecture, I came up with 6.9 as the answer. And I just did it right now, I got 4.431. So now I'm disagreeing with my own self, that's good. All right, 19 divided by 0.492 equals 38.618 roughly is what should be inside of here. Let's take the square root of that. 6.214. 0.713 times 6.214 equals 4.431. Just that. I don't know. 1 minus 0.508 equals, that's 0.492. I don't know. So I'm gonna assume, just for the sake of time, that this is wrong. And what we're doing together here, unless you see something dramatically incorrect in my equation there, assume that this one's wrong, and it really should be, since 4.431 is larger than 2.9. We're going to reject this notion that R is 0. So we're going to assume that there is some linear dependence, so that they are linearly related to one another, and reject that null hypothesis. Right? To be clear, I know it may have been a while since you talked about hypothesis testing, and this stuff maybe has one of those things you try to purge from your memory, but hopefully this stuff rings a bell and sounds familiar. Questions about that? All right, so let's talk about, so regression we'll go through really quickly, because it's not as imperative as, say, just covariance and correlation and stuff are, but they relate, and it's actually good to sort of make sure that they're clear the differences are between them. So let's talk about regression. So how does correlation and regression differ from each other? I mean, we start with that. Just generally, how does correlation and regression differ? Anybody have a guess? All right, so the main thing is that, just to repeat what Dan said, because I sometimes forget that on the recording, you don't hear you. So sometimes you're watching the video back, it'll be me just standing here, absolute silence, nothing, and I'm listening to someone talking in my ear. But so I guess I got to repeat back the questions and be consistent about that. So, or the answers, I mean. So the answer that Dana just gave is that with regression, you can make a prediction, and with correlation, there's not a prediction. It's looking at relationships, which is perfect. Regression has one direction. One way that we typically make, at least symbolically make the difference between them. If I have X and Y, all right, the two different versions of this would be, if I want to indicate that this is regression, we typically use an arrow. This predicts that. All right, there's a directional component. By doing that, I'm specifying that this is the IV and this is the DV. Right? There's an IV and DV. There's a directional sort of component to it. If I don't want there to be a direction, I just want to know if they're related, we typically use then two arrowheads like that, a double-sided arrow, to say that X and Y are related to each other. In a way, it's because we're basically saying X predicts Y while Y predicts X simultaneously. So that's why there's sort of two-headed arrow, right? So it's basically, correlation's a double-headed arrow, or regression's a single-headed arrow. And up here, we don't have IV, DV. We just have two variables that are related. We're not specifying sort of a direction or influence or an IV, DV relationship to one another. All right, so that's the main thing. But the reason I mention this is I want to point out that this difference is a very, very small one. It's a very semantic difference, because we use the same information, just slightly differently, to do correlation and regression. So and they're both based around this idea of covariance. So let's talk about that. So regression, how do we predict one variable from another? So there is this idea of prediction, and we can get things like predicted values. We can go from talking about Y, which is our outcome, to talking about Y predicted, or sometimes we feel like Y predicted, depending on where you learned it from. Where these are the actual outcome scores, and these are the scores as predicted by the regression equation. Okay, so if you're looking at a scatter plot like this, right? The dots here are representing the Y's, right? So we have X's here and Y's there. Right? So all the individual points are correspondence between X and Y. where if we do a regression line through these points, this is y predicted. Right, so it's the points on the line that we predict people would have for y based on x. So these two things are different. There's y, and then there's y predicted. And the difference, let me know what the difference between y minus y predicted is known as. It's the difference, say, between this line, this dot I mean, and this line. So I predict that someone would be here, but in fact they're there, so that difference is called a what? That's right, that's an error. So it's an error in prediction. It was sometimes called a residual. It's like the leftover. So here's what we predict, here's what it is, and that difference is sort of the leftover, the residual, but most commonly referred to as just an error. It's an error in prediction. We predicted this, it was actually that, so we were off by that amount. That's what a residual is. And we can then figure out what the residuals are all the way across and get an idea of, on average, how good of a job are we doing predicting. All right, perfect. So we're oftentimes thinking about how does one variable change as another variable predicts it, or the relationship between one predictor predicting an outcome. But an easy way of thinking about it, because people get really caught up in this idea of like X causes Y. Well, you can't say that because it's regression, it's based on correlation because it's not causal. So instead of thinking about cause and effect, think about it as influence. With regression, we're hypothesizing that X is somehow influencing Y. There's some influence there. There's some relationship between them that is going from X to Y. All right. Most of the time, there are nonlinear regressions, but most of the time when you think about regression, people are talking about linear regression. There are nonlinear forms of regression, like logistic regressions and all kinds of other things, but we're not talking about that. Let's just stick to linear stuff. So it's a technique we use to predict the most likely score on one variable from those on another variable. We try to use the relationship between those two variables to figure out how they relate and then use that to predict one from the other. And the more they are related, the better prediction we can do. So it uses this nature of the relationship, which I have written here as correlation, but technically what it's really doing is using the covariance, the amount of shared variation between them, to then establish this sort of link, to establish a prediction from one to the other. And it does that sort of enhance your prediction. So again, Y is the variable you're trying to predict, X is the variable that's predicting, it's the independent variable, and then all your predictions that we use based on X, we call Y prime, Y hat, different versions of this, but it's all known as sort of Y predicted. Those are the values that are on the actual line in a regression. Why do we care? Right? Well, we may actually want to make a prediction, and we may actually want to figure out things like, going back to our coronary heart disease, and you might wonder why I picked coronary heart disease and smoking. I was trying to think of a very concrete example. This could be, how do we predict things like depression from childhood trauma? All right, so sometimes we can use predictors to predict scores on measures, to actually look at the degree of anxiety or depression or whatever things we want to measure in psychology. It's just I want to use a very concrete sort of example, which is why I use smoking and heart disease. But so we can figure out how fast does CHD mortality rise with every unit increase in smoking. So if you have a country that smokes 9 cigarettes and a country that smokes 10 cigarettes per adult per day, what's the likely increase in coronary heart disease deaths per 10,000? And can we actually predict that change? So we speak about predicting, and usually with regression, we're always talking about prediction, but we oftentimes don't really predict anything. We just sort of establish the relationship, establish that they relate or that they predict, and then that's it. We say, look, the slope is significant, and we just move on. We don't actually predict anything, but you can. There's a way of sort of checking to see if the regression equation is good. It's the same thing that goes for, like if you apply to grad school, when you're applying to college, they use things like GPA and your SAT scores or ACT scores and a bunch of other indicators to predict how well you will do in college or in a university. And they do that without really knowing how your success is going to be. The reason why they're able to do that is they look at past students' performance, and if they scored, their GPA, their SAT scores, and other things all were a certain level, and they were successful in college, you have those same levels as predictors. They're going to predict that you're going to be successful, right? So they're establishing these relationships so they can predict things when they're unknown. But that's oftentimes not necessarily the goal. Usually we're just trying to establish that a prediction exists or that a significant relationship exists, the same way with correlation. So an example, the cigarette and CHD mortality, we can look at the data again, right? So here's the same cigarettes and CHD. We can then establish this prediction line. Right, so this red line here now is the y predicted value, where all the red dots represent the x and y coordinates, which means it's a representation of the actual y values. So this country here only had about 10 deaths per 10,000, but based on this equation, we're predicting them to be more at about 14. Right, so there's actually a difference there in our prediction and reality. There's an even bigger difference here. This same country up here has 6 cigarettes per adult per day, and yet again we're predicting about 14. They have more like 23. Right? So there's an even bigger difference between those two. All right. So here's the typical equation you've probably seen a million times. You may have seen it as y equals mx plus b. What letters go there don't matter. The thing next to the x is the slope. The other thing is the intercept. Doesn't matter what letters people use. You'll see this written in a bunch of different ways, like y predicted equals b1x1 plus b0. Doesn't matter. It's still the intercept. That's still the slope. It could be y predicted equals squiggly thing times x plus other squiggly thing. That's still the slope, that's still the intercept. Doesn't matter what it is. That makes sense? Because people oftentimes will get hung up on, well, I know what is mx plus b, so b is the intercept, and here b is the slope, so I get confused. Don't get confused by that. The thing next to the x is the slope, the other thing is the intercept. Doesn't matter what letter it is they use. Make sense? All right. Plus, these are much harder to write over and over again. Anyway. So, we want to use this equation to predict stuff. Awesome. How do we do that? Well, it really comes down to we want to figure out the slope and the intercept value. Now, you've probably learned, and I'm sure just like I did, going through K through 12 or whatever, even in university, that we used to think of the slope as rise over run. Right? Remember that rise over run? Does that ring a bell? And when it comes to like plotting lines through points, you're like, great, and go up 2 and then over 3 or whatever it is they use to make the line. But in terms of like psychology or for useful practical purposes, what's the point? So how do we interpret the slope? So here's the definition: is it's the change in predicted y, so y predicted for 1 unit change in x. So what does that mean? So how do we interpret that in terms of cigarette smoking and coronary heart disease? How would we interpret the slope? That's right. For every time you go up in cigarettes per adult per day on average, right, the slope's going to tell you how many more deaths per 10,000 you should expect. This is what makes it a linear slope, a linear prediction, because it has a constant rate of change. Going from 9 to 10 is you get B more deaths. Going from 10 to 11, you get the same B more deaths, right? It's the same rate of change regardless of where you're changing in the predictor. It's the same constant level of change, right? So the intercept is a little trickier. So the intercept says the value of y predicted when x is 0. So what does that mean? And how do we interpret that in terms of our cigarettes and CHD example? Sure, like, so if we happen to have or find a country where no one smokes, right, 0 cigarettes per adult per day, what would we expect their value to be? So when X is 0, meaning 0 cigarettes per adult per day, the intercept's going to tell us exactly what we expect their rate of coronary heart disease would be. So in a way, this oftentimes can be interpreted somewhat as a baseline or base rate for things, right? So without cigarette smoking, would we expect 0 coronary heart disease deaths? Probably not. There's probably a base rate for coronary heart disease deaths that even if you don't smoke, you still have a chance of dying for coronary heart disease. So there's sort of a baseline or base rate amount that you would expect, even with 0 smoking, and then smoking sort of adds on top of that. That makes sense? So oftentimes when we look at this, we can see this as a sort of base rate for whatever the outcome is. When you have 0, you have none of the predictor. Okay? Questions? Hopefully this is all completely like old news. Just so bored of it because I've just seen it so many times. So here's the interesting thing. How do we calculate a slope? Well, a slope is the relationship, it's based on the relationship between X and Y. We can think of that in a couple different ways. One, we can look at it as the covariance divided by the variance of X. So remember correlation, go back a second. Correlation was covariance between X and Y over Sx, Sy. It was both of them. So for here, because we want to know the prediction of X to Y, we're taking the same relationship, the same covariance, and just dividing it by the variance of X instead of cross-multiplying the two standard deviations of X and Y. So this is the relationship of X relative to X alone, or this is the relationship between X and Y relative to both. So we're taking the covariance, standardizing it based on both measures. Here we're taking the covariance and standardizing it based on just the variable that we're using as our predictor. That means that the slope, sorry, the correlation and slope are very similar things. They're both based on covariance, and the difference is this one has Y in it, and this one doesn't. So this is relative to X alone, this is relative to both, but they both are measures of how much X and Y relate. It's just this one is bidirectional, and this one is unidirectional. Right? It's going in one direction from X to Y. All right? Yes? So I'm gonna answer that in a simple way and then in a more complicated way. Okay, you ready? Simple way is no. you can apply them whenever the hell you want to. Okay? You can use correlation regression anyway, and that goes for any statistic ever. You can apply it wrong whenever you want. You can apply it to anything. You can do it any time. Now, if the question is, should you use it, for under different circumstances, well, that's a different question. So oftentimes, in order for me to really show that X really does influence Y, right, that there's really this going on, they should be measured at different times. If I measure both X and Y at the same time, then I can arguably make this prediction, but then I can arguably make the other one too. Well, maybe it's Y that's predicting X. Those are both perfectly logical because they're both measured at the same time. So one of the things to establish cause, or at least to strengthen your prediction, is to establish something called, this is going outside of the class, by the way, temporal precedent. That one comes before the other temporally in time, right? So in those cases where you have temporal precedent, it makes more sense to use regression than it does to use correlation. Make sense? If there's no temporal precedence, like where they're both measured at the same time, no matter what you're doing, even if you're doing regression, if you're doing prediction, you're really just doing correlation. Right? Even if you say that X predicts Y, well, you're testing that, but there's no real reason other than you're just doing that to establish that that's the order of the direction. That doesn't mean you can't use regression. You can use regression even if they're measured at the same time. It's just the interpretation of what the slope really means, or how meaningful that slope is, gets diminished without something like temporal precedent. So this is like a different class. You do like they might talk about it a little bit in like 100B or whatever your research methods course is in terms of how to establish sort of a causal link between variables. One of those things is temporal precedence, even though they may not have called it that, but there should be some temporal ordering to variables in order to establish a stronger link for why that order is the way it is. So even if I'm doing a slope, and regression between two variables measured at the same time, it's really still just correlation. You're really just looking at how the variables are relating, because you can't really establish temporal precedent to really say one predicts the other. That makes sense? We're getting into like the weeds and the super complicated. So that's why I said the easy question is, no, it doesn't matter. You can do correlation or regression whenever you want, because they're really, are both doing the same types of things. It's just if you have temporal precedent between X and Y, it makes a lot more sense to look at the prediction of X to Y than it does just to ignore the temporal precedent and do a correlation. So I told you there's like the easy and then the more complicated. All right. So because of the link between between correlation and slope being the covariance, if we actually have the correlation, we could simply multiply it by this ratio of their standard deviations and convert the correlation to a slope. So if I were to take the correlation here and multiply it by SY, SX, what that does is this cancels the S's out, and then these now multiply each other, and it converts it to covariance of XY to SX squared. Make sense? So that's why you can convert any correlation to a slope by simply multiplied by this ratio of standard deviations. One of the things that you'll notice about any points that go through let me go back actually this way. Any line that goes through the points, right? So I can think of any number of lines I'd like to go through these sets of points that all of them would work pretty much okay. There'd be obviously some better or worse ones. But I could draw it slightly differently, going this way or something, right? I can draw different lines, but all look pretty much okay. But the one thing is, right around here somewhere, there's going to be a point where you're going to have the X mean and the Y mean. It's going to show up at some point where any line you want to draw through these points, doesn't matter what it is, will have to pass through the point where the means of X and mean of Y are going to cross, which is sort of like a pivoting point for all the lines that are going to go through these points. It's going to have to pivot somehow on that one point where X and Y means cross. Because of that, we can use that to our advantage to figure out then what is the intercept. So the idea here being, let's start at the point, start at the X mean, work our way backwards using the information from the slope and the Y. Start at the Y mean, we use the information we have from the slope and our X mean to then work our way backwards from where the point, the line will actually cross the Y intercept and give us the intercept value. So, back in K through 12, we worked on, again, maybe in university, we used to draw these points. We had to figure out the intercept so we knew where to start. This is actually a bad example because this example this isn't at 0. We'd actually have to back it up a little bit further to figure out the real intercept value wherever this point becomes 0. That makes sense? This really is the part where the line crosses the y-axis, but the y-axis should be at 0 and 0. Right now it's at 2 and 0, so it's a little bit goofy. So we'd have to go back a little bit further to figure out that the real y-axis at 0 is here, to figure out that here's our intercept value, the point where the line crosses the y-axis. We can get there by starting here, starting wherever the x mean is, let's say it's here, and just working our way backwards to that point. And that's what that A equals y bar minus b times x. Make sense? We're just sort of working our way backwards to the intercept. The reason I'm pointing out this whole thing with 0 is if you actually, when we compute the intercept value, it looks like it's going to be something like 6, but it's not, because this is not really the y-intercept value. This is a little bit misleading. This graph comes out of SPSS, and they do weird stuff like that by making the graphs sort of shrink them in and make them look better or something. I don't know. I didn't notice that until just now. So let's figure out then what these values would be for our example. So if, all right, we got our covariance is 11.126. So we start there, 11.126. 11.126. It's supposed to be an 11 over. So if our standard deviation for x is 2.334, I just squared it and got 5.448. So that's our variance for x. Divide those, what do you get? .04. Is there a third decimal? 2.04. Cool. Just keep everything at 3 decimals. Anyway. All right, so that's that. Now that we have that, we can then take the y mean, which is 14.524. 524 minus our slope, 2.042, times our x mean, which is 5.925. What do you get? The one downside to this setup is these markers are super squeaky. It's like constant noise the whole time you're writing on these things. It's kind of annoying, but anyway. $2.425. May else get that? Can confirm. Just to make sure. Yeah. Yeah, so I mean, it really should be this squared. Sorry, so yeah, so I took, if you go back a little bit, I took the standard, you had to go back actually quite a bit, but just to connect it in your brain where this is coming from, I took the number here, 2.334, down here, which is the standard deviation for x, right? So I meant to, that part of the slide was meant to say, so the variance for x, which is what we need, the s of x squared, is just the s of x. How far we go? Somewhere close, we're getting there. Here. It's really just the s of x, 2.334 squared. I just didn't put the 2 there. Is 5.448. Yeah. So we're good? 2.425 is the answer? We're good? Okay. So with that, we can then create a prediction equation, which means I can take y predicted equals my 2.042 times x plus my intercept value of 2.425. So now let's go back and interpret. If we found a country in which the average adult did not smoke, there were 0 cigarettes per adult per day, what would we predict that country, what rate of coronary heart disease would we predict for that country? That's a mouthful. Yeah, you don't have to plug anything in at this point. You should be able to look at it and tell me based on just the equation here. So basically, if we had 0 cigarettes per adult per day, which is what X is, as 0 here, we predict what for Y? 2.425. Yeah, this is why the intercept value is the value for Y predicted whenever X is 0. It's basically our base rate value. So we'd still expect, even if everyone didn't smoke, no one smoked in a country, there's still a rate of coronary heart disease deaths we would expect per 10,000. Now, as you go up every unit, you go from a country that has 0 to 1 cigarette per adult per day, we'd expect an additional 2.042. So you add those together and you get 4 point something or other coronary heart disease deaths per 10,000. If you go to 2 deaths, you add this again. So every time we go up a single unit in X, we're expecting another 2.042 deaths per 10,000. Makes sense? So this is the rate of change. This is our base rate of change. Which is why when I mentioned a second ago about this graph being a little bit misleading, because again, it looks like our intercept is something like 6. That's because this needs to come out all the way to 0, where it's really more like 2, right? So it's a little bit misleading in this graph, but so this is still considered, the point. Hitting the wrong button. Sorry about that. It's still considered the point where the line crosses the y-axis. That's still accurate, but that really only is useful if you're just literally trying to draw out a line through points and use rise over run to sort of graph things out, which is great, but not super useful when it comes to research of psychology and that kind of stuff to try to use regression to test out hypotheses. This does tell us something interesting, that when you have 0 cigarettes per adult per day, we don't expect 0 deaths. So cigarette consumption is not necessarily the only thing contributing to coronary heart disease. There's other things going on. There's still a base rate even when cigarettes aren't involved. And for every additional cigarette per adult per day, we're expecting another 2 deaths, roughly per 10,000. Questions about that? We can then use this to actually calculate what numbers go on the line. All I have to do is figure out an X value, like 4, plug 4 in to this equation. Actually, I can leave it back on this slide over here. I can plug 4 into this equation, multiply by 2.04, add in 2.425, and it'll tell me the number that is on this line. It'll tell me the number that I predict for that country. If I plug in 6 cigarettes per adult per day, I'm going to get the point in the line that's for 6 cigarettes per adult per day, right? So this equation tells me what numbers fall in this sort of linear prediction. Right? Questions? All right. Let's go back to where we were. Last couple things I want to mention is that we can actually use this stuff to make predictions. So we don't have a country that has 10 cigarettes per adult per day. If that country doesn't exist, at least not in our data, right? Let's go back and confirm that for a second. So look, if you go back to here for a sec to the data points, oops, too far. So it goes from 11 to 9 to 8 to 6. So there's no 7, there's no, there's a 4, 3, yeah, there's no 7, no 10, no 2, no 1. The idea is being, if we were to come across a country that had 10 cigarettes per adult per day, what would we predict their CHD deaths to be? So we simply plug the numbers in. So I can plug in equals, what was our slope again? 2.042, I think, times 10. Add in the 2.452. Do I remember those correctly? I just realized I erased them. I didn't write them down anywhere else, so hopefully those are them. Is that right? 2.042 and 2.452? Ah, okay. Little dyslexia kicking in there. All right, 425. Like that. And we just plug it in. So what's 2.042 times 10? All right, well, that makes this 20.42, right? Plus 2.425. We get 22.845, I think. Something like that. So that means we predict, roughly, if we had a country with 10 cigarettes per adult per day, we predict roughly 23 deaths per 10,000, somewhere in there. And again, we don't have that information because we don't have a country with 10 deaths. But if we did, right? So it makes sense. It's somewhere between 21 and 26. Somewhere between, the values that are for this country and this one up here, these countries and this one up here. So 23 makes, sense somewhat as a good prediction. So we would guess somewhere around 23 deaths per 10,000 if a country had an average cigarette consumption of 10 cigarettes per adult per day. Okay? So with this one, we don't have a country that has 10 cigarettes per adult per day, so we have nothing to compare it to. So this is just a guess. This is just a prediction. But if we actually had, I think I have that on this next slide. Nope. Let's back up a second. If we did, because I mentioned this, but just to reiterate, if we did, let's say instead I made this for 6. So we do have a country that has 6 cigarettes per adult per day. So 6 times 2.042. 6 times 2.042 equals 12.252 plus 2.425 equals 14.677. Okay, so this would be not for 10, but for 6 cigarettes per adult per day, right? So we predict roughly 15, somewhere in there. So the reason why I mention this is because we do have a country, 2 countries, I think, that have 6 cigarettes per adult per day. So one of them scored an 11, the other one scored a 23 in terms of CHD mortality, right? So we can actually then figure out what are the residuals for those countries. So I'm actually going to erase this so you can see it. So we know that that's my predicted value, 14.677. So that means for one of those countries, for 11, so if I take 11 minus 14.677 and 23 minus 14.677, I'm going to get 2 residuals. So it's 11 minus 14.677. I don't know what's up, man. So negative 3.677, and what about 23 minus that? So those now, so these are residuals for, for 6 cigarettes per adult per day. Right? We over predicted for one, under predicted for the other. So we could do this by creating a Y predicted for every single country, going through and putting those predictions down here, subtracting and getting residuals. So residuals tell us sort of how good or bad we are. We can square those residuals, add them up, and divide by n-1 to get a residual variance, and then divide that to get what's called a standard error of estimate, which is basically a standard deviation for errors. So it's a typical way in that we sort of judge how good predictions are is by looking at, well, not only, is there a prediction that's significant, but also how tight are the errors around the line? How good a job are we doing without being sort of over and underestimating things too largely? Maybe we can do that by calculating the residual variance and then looking at something like the standard error of estimate or something like that. But I don't want to get too far down that rabbit hole. I want to keep going forward to other cooler, better, interesting stuff. So with correlation and regression both, you can get measures of something called, I mentioned this before, the R squared, which is called, it's a correlation square, but it's oftentimes called the coefficient of determination up there. And the reason why it's called that, it's basically how much variance in one variable, like y, can be determined by the other variable, by the predictor x. So if we take r and square it, it gives us the percent of overlapping variance, or how much variance do those two variables share. Okay, so we did it before where we took, point, actually I think it's on the next slide, 0.713 squared, which was in that earlier t-test formula, was 0.508. So that tells me approximately 50%, really 51% if you want to be super accurate about rounding. Roughly 51% of CHD mortality is associated with smoking. So it doesn't mean that it's not like determinism where there's 50% chance. It just means that of the variability in coronary heart disease deaths across these 21 countries, the variability in smoking in cigarettes per adult per day accounts for or overlaps with 51% of that variability. So they share 51% of their variability, which is quite a lot. Right? So half the variability in coronary heart disease death is shared with cigarette smoking per adult per day across these countries. So it gives an idea of sort of how much overlapping variance they have, how much they relate. And because of that, I think I have the last thing here, you can take 1 minus that number, this 0.429. This is oftentimes, I love this, the coefficient of alienation. It sounds so much worse. Coefficient of alienation, or sometimes they call it just of non-determination. How much variance do they not share? How much variance is alienated from one another? So there's roughly 49% of the variance that is not shared. So if they share 51%, they don't share 49%. So you oftentimes will see what this is associated with when looking at the relationship between x and y, how much error variance is there? So there's predicted variance. There's about 51% predictive variance and only about 49% error variance. This is the variability that they do not share with one another. So it's all in error. Okay? Just terms, things to make sure you have that you maybe remember or seen for the first time. Questions about those? So I want to get to the real meat of stuff. This is the next topic. So, I mean, you can't really say anything about it being directly related in terms of, like, you got to stay away from anything that remotely sounds like cause, right? So it's not a causal relationship. It's just as things vary, think about it sort of visually, right? You have X and you have Y, whatever those things are. There's a certain amount of variability that this has, right? And then there's a certain amount of variability that this one has, corresponding to the same people having taken both. Actually, this could be a lot tighter even. So they don't necessarily have to even be the same amount of variability. It's just, it's how much of the variability between these two things are overlapping. Again, it goes back to the idea of correlation. What percentage of scores are both above the mean, both below the mean, right? They tend to follow the same pattern relative to the mean of each of the two variables. So in this case, I just realized it's weird. So this is green. This is orange, but it doesn't look that way. Do you see green and orange, or do you see green and green? Yeah, they both look kind of green, right? So to me, on my side, it's like distinctly green and orange, but on the screen, you don't see the orange very much. It looks very much green. It's weird. It must be something about how the color is dialed in on the camera. I may have to fix that. It's odd because you can't really tell the difference. Or I just may have to not use orange or something. Anyway, sorry, I got distracted by the colors. Anyway, because we know the correlation is 0.713, again, it's a little bit it's a little bit difficult to interpret that directly. We know it's sort of big, but other than that, it's sort of hard to gauge. But if you square it, and it gives us this idea of a percentage, a correlation of 0.713 tells us that 51% of the variability is sort of following the same pattern across the two variables. And that's something that's a little easier to interpret. They share 51% of their variability. All right. All right, let's move on. Any other questions about this stuff? Let's go on to some other cooler topics, new things.